How many joules of energy are needed to change 10 grams of ice at 0 degrees to water at 20 degrees? Now we only have two steps. First, you must melt the ice from solid ice to liquid water at 0 degrees. Then you heat that liquid water from 0 degrees to 20 degrees. And melting the ice took 3,350 joules. And raising the water temperature took 837 joules. For a total of 4,190 joules, or 4.19 times 10 to the third joules. And again, they're going to 3 sig figs. Because this is an addition-subtraction problem. This number is plus or minus 10. This one's plus or minus 1. This is sloppier, so their answer goes to the plus or minus 10s. Intermolecular forces. These are the attractive forces between molecules. These forces allow for the formations of liquids and solids. The degree of intermolecular forces correlates with the compound's physical properties. Let's see here, our point is still floating. So again, water has a huge amount of intermolecular forces. We'll put another one in there. Two. Put a third in there. So again, water is an extremely strong liquid. It has extremely strong intermolecular forces. You can hold up things that are denser than water, actually, because those molecules bind so tightly to each other, they won't let go. And that actually gives water a lot of its unique properties. Again, the stronger the intermolecular forces of a liquid, the higher the boiling point and the lower the vapor pressure, which is why water has a pretty high boiling point compared to most liquids of its size. Water has dipole interactions and also, even more important, hydrogen bonds. But we remember from previous chapters that oxygen is a lot more electronegative than hydrogen. And therefore you have this negative charge here, then you have a positive charge here. So every water molecule has a dipole, has a partial negative and a partial positive. And those forces bind them together. But also, there's a special force here, the hydrogen bond. If we look at the group 6 hydrides, you would expect water, if you look at this trend, you would expect water or ice to melt at negative 105 Celsius. And you'd expect it to boil at about negative 80 Celsius. But it doesn't. It does not melt at negative 105. It doesn't melt till 0. And it doesn't boil at negative 80. It boils at positive 100. And so you notice that water does not fit in the trends. With all the other ones, they start increasing just because the molecule is getting bigger. So from sulfur to selenium to tellurium, the atoms are getting bigger. You're having more van der Waals forces, and so you're seeing the boiling point going up. But water is way higher than all the other ones. And that's because water has hydrogen bonding. Hydrogen bonding is a specific force that occurs between a protic hydrogen, meaning a hydrogen on something besides carbon. It's a hydrogen that can pop on and off. And it can hydrogen bond with nitrogen, oxygen, or fluorine. Only nitrogen, oxygen, or fluorine. If you're ever looking at a pharmaceutical compound and you see a fluorine, take special note. It's there on purpose. Fluorine chemistry is extremely difficult and extremely dangerous. You don't use fluorine unless you absolutely have to. But it's useful because it can make molecules bind tighter into pockets because you have an extra hydrogen bond there. So hydrogen bonds. Water can make 4 hydrogen bonds. Hydrogen bonds aren't super strong on their own. They're like 5% the strength of a covalent bond. But there's strength in numbers. There's so many of them that it adds up quite a bit. And because of that, it's overall a very strong force. So this hydrogen can hydrogen bond. Hydrogens on carbon do not hydrogen bond. For a hydrogen to be able to hydrogen bond, it has to be on something besides carbon. Carbon just holds it too tightly. But if it's on an oxygen or a nitrogen or a sulfur or a selenium, it can pop on and off and is capable of being a part of a hydrogen bond. And again, hydrogens can hydrogen bond with fluorine, oxygen, and nitrogen only. So which of the following molecules would be expected to participate in hydrogen bonding? Well, only one of them has both the protic hydrogens and an NO or F, and that's methanol. Acetonitrile, the only carbons or the only hydrogens are attached to carbon. Those will not hydrogen bond. Here we have a little piece of Teflon. There are no hydrogens. Here we have a nitrogen, but all the hydrogens are attached to carbon. They will not hydrogen bond. However, in methanol, the protic hydrogen that's attached to the oxygen can absolutely hydrogen bond. So, molecules without dipoles can also interact with each other. These are the London dispersion forces. So imagine we have 3 atoms. These are sulfurs. And they all have electrons. And those electrons are all moving around completely randomly. If, for no particular reason, in one of these atoms, all the electrons move over to one side, temporarily, you get a negative charge there. So just let's say randomly, a bunch of the electrons moved over here. This side of the atom becomes negative, this side becomes positive. But that affects the atom next to them. This side becomes negative, this side becomes positive. That affects the atom next to it. This side becomes negative, this side becomes positive. And now that's always going to be changing, because now the electrons may all move over here, making this side negative, this side would be positive, this side would be negative, this side would be positive. And so the London dispersion forces are due to the transient, ever-changing negatives and positives that occur in an atom, just because the electrons are negatively charged, and the electrons are moving randomly, which means sometimes there's more over here than over there, and you have a negative side of the atom. The bigger an atom is, the more electrons it has, the more opportunity there is for van der Waals forces. So London dispersion forces, also called van der Waals forces, are completely due to the transient positives and negatives that occur in atoms due to the random chaotic motion of electrons. They're always changing. As the atoms get bigger, you get more of these forces. And so if we look at the hydrocarbons, methane, ethane, propane, butane are gases. Now it gets bigger to pentane, and all of a sudden it's a liquid. It's a very volatile liquid, but it's a liquid. Then hexanes, heptanes, octanes are like gasoline. It runs just like water. But as the molecules get bigger, we'll end up with oil, like thick oil. It becomes viscous. You have even bigger molecules, you end up with tars, a semi-solid. And you have even bigger molecules, and we end up with asphalt. And so the difference between natural gases, gasolines, oils, tars, and asphalt, they're all hydrocarbons. It's just how big is the molecule. The bigger the molecule, the more van der Waals force is present. So in this question, they ask which molecule would have the largest London dispersion forces. Just look for the biggest molecule. C15 is the biggest. It will have the biggest London dispersion forces. That's completely size-based. If we look at our halogens, fluorine is a gas. Go down to chlorine, a much heavier gas. Bromine is now a liquid. Iodine is now a solid. The only difference is the amount of van der Waals, London dispersion forces, that are occurring as it gets bigger. Hydrates. We'll do this in lab next week. Hydrates are solids that contain water molecules as part of their crystalline structure. The formula lists the anhydrous formula, and then a dot, and then how many waters attach. So for calcium chloride, 2 molecules of water will bind to every calcium. And every molecule is different. Copper 2 sulfate will have 5. Iron 3 chloride will have 6 waters that will bind to it. Sodium chloride has 0. Table salt doesn't collect water. Epsom salts, magnesium sulfate will have 7 waters bind to it. So it's always heptahydrate. A lot of times the color comes from that binding to the transition metal. Transition metals are the D block. They have D block orbitals. And binding to d-block orbitals typically has light wavelengths in the visible light range, and so they form pigments, and you can see them. And so like the salts of group 1 and group 2 elements are always just white. But the transition metals, that's where you get your colorful stuff. And we see here that the blue in copper 2 sulfate is actually coming from the water binding the copper. And so when the water binds the copper, you get that blue color. Calculate the percent water in Epsom salts. Make your life simple and pretend you have 1 mole. We find the total molar mass of magnesium sulfate heptahydrate. Remember, the 7 waters are part of the formula. You've got to have them in there. And then we just take the mass of the water, 7 times 18, divided by the total mass, which included the water. And we see that when you have Epsom salts, 51.16% of the mass of Epsom salts are actually the water that's trapped in those crystals. So if you heat it up, that water will escape. You'll be left with only half of your mass. Any questions? Questions at all? All right. What is the percent water in copper 2 sulfate pentahydrate? Again, pretend you have a mole. Find the total molar mass of the compound. That includes the 5 waters. And now you take just the mass of water divided by the total mass, which also included the water. And we see it's 36.08% water by mass. Water is a unique liquid. It covers 75% of the Earth's surface. 97% of Earth's water is in the ocean. And water constitutes 70% of the human body by mass. It is colorless, odorless, and a tasteless liquid. And it's unusual in that it is more dense in the liquid phase than it is in the solid phase. And that's actually because of the hydrogen bonding. The hydrogen bonds are so strong that when it freezes, it adopts a very open crystalline structure that's about 10% less dense than liquid water. So ice will always float, which is absolutely